For today's lesson, we're going to look at some visual representations of expressions. When we worked at our anchor problem, our cell phone problem that is, we talked about several different ways to represent problems. In the case of our anchor problem, we had our cell phone plans, which were represented by an actual equation. For example, plan number 1 was represented as the cost of plan 1 in relation to the number of messages was equal to 0.1 m plus 30. We then talked about this same equation, but written out as a verbal expression. We interpreted it as 10 cents per message and a monthly fee of $30. The final way we looked at interpreting our cell phone plan problem was that we looked at graphs, and we developed a graph for cell plans that graphed all 4 of our different equations. If you remember, it looked something like that. Today we're going to look at the visual representations of some of the expressions that we've been building. So let's start by reviewing building expressions. We have 2 examples, 7 times the sum of a number and 6, and 3/5 the sum of a number and 9. So, as we discussed before, we need to break it down into pieces. The top problem can be broken down as so. The sum of a number and 6, and then 7 times. When we work it out together, we'll get 7 times a number, represented by x, plus 6. Because remember, sum means addition. Our bottom problem can also be divided into several sections. We have, again, the sum of a number and 9, and 3/5. In this case, our problem can come together like so. A variable x plus 9 multiplied by 3/5. You'll notice that I'm multiplying by 3/5 even though there's not a word here that specifically says so. You will often see the words 3/5 of the sum of a number and 9, but not always. So you'll have to use your best judgment as to how to interpret some of these problems. Next, let's take a look at what we can do to visually represent some of these problems. Let's start by thinking of these problems as a box, or a rectangle in this case. We're going to work with the first problem, 7 times x plus 6. Because our problem does not have 2 variables, we can't graph it on a coordinate plane. In order to graph something on a coordinate plane, you have to have 2 variables, which is why last year you learned that the proper way to graph an equation was to look for something in this format, y equals mx plus b. In this case, the value of y is equal to the slope times the variable x plus b, which is our y-intercept in this case. Now, as we look at this, we're going to instead think of this box as a representation of area. Area is length times width. If we look back to our original problem, 7 times x plus 6, we can see that we have 2 pieces multiplied together. So in some cases, we could say that we have one value multiplied by another. So we can take this and relate it back to our area. In our shape, I'm going to say that the short side represents width and the long side represents length. As we look back to our original problem, I'm going to decide that 7 represents my width and x plus 6 represents my length. If you think about area as being length times width, the area of the rectangle shown is now 7 times x plus 6, or the length times the width. So all of the area in here is equal to the answer to our problem. Now let's look at a slightly different way of building our rectangle. We start with the same rectangle, but now I'm going to divide it into two pieces. We have block number 1, where the area is shown in red, and block number 2, where the area is shaded in blue. I'm still going to say that the width is 7. But now I'm going to say that the length of the red piece is x, and the length of the blue piece is 6. To find our area, we still need our length and our width. We know our width is 7, but now we have to determine the total length. To find the total length of our rectangle, we have to combine the two lengths of the red and the blue piece. In this case, we could simply say that if we combine them with addition, we have the total length. This results in the same length as the box above, where the total length is x plus 6. So once again, if we were to multiply our width of 7 by our total length of x plus 6, we come back to our original equation. These rectangles start to let us examine new ways to build visual representations of our problems. So let's look again at a slightly different problem. We're starting with a rectangle, again divided into multiple pieces. We'll have a blue section, and we'll have a green section. The width of this rectangle will be 4/5. The length of the blue section we'll call x, and the length of the green section we'll call 4. From a representation like this, we can determine the original algebraic expression. To start, we'll determine the total length of our rectangle. Since we know that it's the sum or the combination of the individual lengths, we can say that x plus 4 is our total length. Our width is still located here on the shortest side. In this case, this visual representation shows the expression 4/5 of x plus 4. So from this way we can find the equations or expressions from the picture. Finally, let's look at a different way to build our expressions. In the previous example here, we had 4/5 x plus 4. So let's build that same rectangle one more time. We have a width of 4/5, a length of x, and a length of 4. This time, we're going to think about the area of the green section and the area of the blue section. We determined in the last problem that the area of the black rectangle was the total length times the total width. Right now, we're going to look at what the area of the small green section and what the area of the blue section are. Since the black rectangle is made up of the green rectangle plus the blue rectangle, then we know that the area of the black rectangle has to be equal to the area of the green rectangle plus the area of the blue rectangle. Using this information, we can find our total area. The area of the green rectangle is found by finding the length times the width of the green space. In this case, it is 4/5 times x. The area of our blue space is found in a similar way, length times width. In this case, 4/5 times 4. Let's simplify these two equations. 4/5 times x can't be simplified any further, so we'll leave it as 4/5 x. 4/5 times 4 can be simplified. In this case, we'll remember that when multiplying fractions, we have to turn our non-fraction into a new fraction by putting it over 1. Now we can multiply straight across. So our result is 16/5. Since we know that the total area of the black rectangle is equal to the sum of the green and the blue rectangles, we can add them together. The area is equal to 4/5 x plus 16/5. This gives us our total area for this problem. If we come back here to the original problem and we were to distribute our total area, we would find that it would be the same as 4/5 x plus 16/5. So once again, we found the same information from a different method. Using this method, we can find the area of any one of these rectangles and as a result, determine the equation or expression that represents the picture.